sorry, this is problem set 4, exercise 2. So in this exercise, we have a k-regular undirected network, okay? And we have to prove first that the vector of ones is an eigenvector of A, where A is the adjacency matrix of this regular graph. Remember that a k-regular graph is a graph where all the degrees of all the nodes is equal to k. We have to prove also that there are no other eigenvectors with all components positive, and in this case, I have to use the Perron-Frobenius theorem. Then we will have to calculate the cut centralities, and then we are going to try and find if there are any non-homogeneous centralities. Non-homogeneous meaning that we actually can rank the nodes, because we are going to see that the eigenvector centrality and the Katz centrality, both centralities are homogeneous. They are exactly the same for every node in the network. So it's not useful for ranking. So let's start with the first question A. Okay, so now 1, they tell me that 1 is an eigenvector of A. Well, this is quite simple, because if A is k-regular, this means that the degree of every node is equal to k. That's what it means. And now, how can we compute ki? Well, ki really is the addition of all the columns for each of the rows of A. Okay, so if we are in row I, so we are focusing in the degree of node I, then we are going to find that this addition is this is the definition of how to compute the degree with the adjacency matrix. Okay, so this is how we can check that really this is the case. So so let's say that the addition of Aij, this is by definition, this is equal to ki, and this, because this is a k-regular network, this is equal to k. So when I multiply matrix A times the unit vector, not the unit vector, but the vector of ones, this is equal to, I'm going to do it component by component. Okay, so the ith component of this vector is going to be the addition in J of Aij times 1, which is exactly the expression that we had before. So this is equal to so this is equal to ki, which is equal to k. So since this is the same for every row, then what we have is that A times 1, this is equal to k times 1. So we have that 1 is an eigenvector, and the eigenvalue associated to this eigenvector is k. Okay, and that's it. Now on question B, we need to show that there is no other eigenvector that has all the elements positive, and we have to use the Perron-Frobenius theorem for this. So the Perron-Frobenius theorem, since A is a matrix of the adjacency matrix of a connected network, okay, so I can use the Perron-Frobenius theorem, which states that the largest eigenvalue, okay, the largest eigenvalue of A, this largest eigenvalue, we know that is going to have, okay, this is unique and real. Well, largest on the, well, in this case, yes, because it is a symmetric matrix. It is unique and real. More things. We also know that the elements, okay, there are eigenvectors. Okay, this largest eigenvalue is going to be R, okay, which is the Perron-Frobenius eigenvalue. There are eigenvectors with all components positive, and this is very important. There isn't any other eigenvalue with an associated eigenvector with all the elements positive. Okay, so this only happens for this eigenvalue. So this is the thing that they're telling me. The only thing that we need to prove now is that k, lambda equal to k is the Perron-Frobenius eigenvalue. That's the thing that we need to prove. But we also know from the Perron-Frobenius theorem that the Perron-Frobenius eigenvalue is going to be bounded by these two quantities. So it is between the minimum, so it's going to be between the minimum in I of the summatory in J of Aij and the maximum in I of the summatory in J of Aij. This means that it's going to be between K-min and K-max. Okay, this is basically the idea. So in this case, since K-min and K-max are the same, then the Perron-Frobenius eigenvalue has to be equal to K. So what we have is that the Perron-Frobenius eigenvalue is the largest one in the matrix, and also the vector of ones and all proportional vectors to this vector are the eigenvectors of this eigenvalue, and these are uniques. Okay, so there is no other eigenvalue. I mean, this is a simple eigenvalue. It's not repeated. Okay, so we have only multiples of one that can be eigenvectors with this eigenvalue. Now, the problem of obtaining this result is that the eigenvector centrality is going to be the same for all the nodes in the network. So, because the eigenvector centrality basically is going to be proportional to 1. So, we don't want that. I mean, we need a centrality to make ranks. And if we have the same value for all the nodes, then we cannot rank them. Let's see, in question C, they ask about the cat centrality. So we are going to calculate the cat centrality. So the cat centrality is the following, is the one that goes solving this equation. Okay, so this is the equation for the cat centrality. If we write this in a vector notation, here we have that x vector, it's equal to alpha times x vector times A. Remember that this J is the same as the first index of this matrix, so the multiplication is on the right when we write it in vectorial form. So x is a row vector, really, and this is a 1 vector. Okay, so remember that this 1 vector is also a row vector. Okay, so we have that all the x's are rows, and also this vector of ones, they are also rows. Now, in order to solve this, we need to clear, okay, the value of x. So we are going to write this here on the left, and then we are going to take x as a common factor. So taking x as a common factor, it gives first the identity matrix, because when I mean x is the same as x times the identity matrix. Okay, so that is how I can get this. Is like the 1 if I were using numbers, and this is minus alpha times A. Okay, and this has to be equal to the vector of ones. Now this is the equation. So the solution to this equation, if alpha is not if this is an invertible matrix, okay, if it is non-singular, then we have that x is equal to the identity minus alpha A, the inverse, times 1. Okay, now the question is, what is this value going to give me? Do we know how much is, what is the result of this calculation? Well, the answer is yes. because because this matrix is really related to matrix A. So the point is that with this, we are going to see, now I'm going to talk a little bit of what happens if I know that we have an eigenvector v of A, which is equal, when I do A times V, sorry, I'm going to do it on the left. It doesn't matter in this case because A is symmetric, but well, I'm going to do it on the left side. So if I have a row vector V times A, then this has to be equal to lambda V. So let's see what happens now with the matrix I minus alpha A. What happens when I multiply this vector, I mean this matrix, by the row vector V. So the result is going to be V minus alpha V times A. And alpha and V times A, we know that is alpha V. So this is going to be V minus alpha lambda V. Okay, so in the end, this is going to be also a multiple of V. So the result is proportional to V, just like in an eigenvector equation. Now the matrix is B, so we have that V times B, matrix B, it's equal to 1 minus alpha lambda times B. So we have that the eigenvalues of this new matrix B are going to be related to the previous eigenvalues of matrix A, but the eigenvectors are going to be exactly the same. So if I have an eigenvector of A, it is still going to be an eigenvector of the identity matrix minus some constant times A. Okay, so this is the matrix that is going to have exactly the same eigenvectors. Now the point is that here we don't have exactly that matrix, we have the inverse of this matrix. Well, we are going to see another example, another result from eigenvectors, okay, which is the following. If A is diagonalizable, and being diagonalizable means, okay, is equivalent as saying that there is some matrix P and some diagonal matrix D such that P is non-singular, okay, I can calculate the inverse of P. So I can write A like this. So if I can write A like this, it means this is exactly the same as saying that A is diagonalizable. Now the point is that A comes from an undirected network. So A is diagonalizable, okay, that's the point. So in our case, what we have is that, let's see now what happens with the inverse, okay? So when I compute, if A is invertible, okay, if A to the minus 1 exists, and remember that this happens always when the determinant of A is different from 0, okay, then I'm going to calculate the inverse of this expression. So the inverse of this expression is the multiplication of the inverses, but changing the order. So I'm going to write the inverse of this first, then the inverse of this, and then the inverse of this. So when I write this, I write the inverse of P to the minus 1, then the inverse of D times the inverse of P. And the inverse of the inverse is P, so this is P times D to the minus 1 times P to the minus 1. So this is telling me that A to the minus 1 is also is also diagonalizable, but not only this, because here are this matrix P is exactly the same, and the matrix P is the one that has the basis of eigenvectors of A. Okay, this is a basis of Rn, which is composed by eigenvectors of A. So the thing is that since they both have the same matrix, they have the same eigenvectors, okay? So P the same, it's equivalent as saying that they have the same eigenvectors. So if in this case we were talking, instead of A, we were talking about this matrix here, okay? So this is the matrix now that we want to that we want to know the result when I multiply this by 1, then by the way, the eigenvalues are going to be the ones that are in the diagonal of d to the minus 1, which are 1 over lambda I. Okay, so now we have that the eigenvalues are the inverse of the previous ones. That's it. So what we find is that x, which is equal to, according to this expression, the identity matrix minus alpha A, the inverse of this matrix, times the vector of 1s. Since 1 is an eigenvalue of A, okay, we know that A times 1 it's equal to K times 1. And we also know, no, this was, sorry, my mistake. Yes, because this, I have to multiply this on the right. Sorry. So this, I mean, it's going to give the same result because this is a symmetric matrix. Okay, so yes, but yes, but we have to do it properly. Okay, so this is I minus alpha A to the minus 1. My mistake, sorry. It's just because I'm so used to multiplying on the right that I always do that. In this case, the result is going to be the same because this is a symmetric matrix, but it doesn't have to be the case. In this case, what we have is that, okay, so now our formula is x equal to 1 times that matrix, okay? And since we know that 1 times 1 minus alpha A, this is equal to, this is going to be equal to 1 times 1 minus alpha K, okay? Remember that K is the eigenvalue related to this eigenvector, times, yes, that's it. So this means that we have that 1 is an eigenvector of this matrix, so it's going also to be an eigenvector of the inverse of this matrix. And remember that the eigenvalues are going to be given by the inverse of this eigenvalue. So this is going to be 1 over 1 minus alpha K times 1. Okay, that's it. So the point is that this result is also going to be proportional to 1 because this is a constant which is going to be the same for all the components of this vector. So in the end we have that the cut centrality is homogeneous. Homogeneous in the graph, which is no good for a centrality measure. So instead of using any of these, let's see what we can do. Now on question D, that's exactly what they're asking. They're asking to name a centrality measure that could give different centrality values for different vertices in a regular network. Now the point is that we have used centrality measures which are related to linear algebra, which are very nice, but in this case it's not the most appropriate. But we have some very simple centrality measure like the closeness centrality. And betweenness centrality. That we haven't tried. So in order to check this, I'm not going to compute it just like this because it's going to be very, very long, but you can imagine we are going to assume that we are building like in the case of the Watson-Strogatz model. Okay, remember that we start with a regular lattice in a ring form. Okay, so here we have that all nodes are joined with the nearest neighbors, but also with the next ones. Okay, so with these ones, and if we wanted to add more, not only k equal to 4 but k equals 6, then we could also join to the next ones, and so on. So every node is going to be joined to is going to be directly linked to the k-half nearest nodes. That's the idea. Now this is going to be a regular network. And since we have that all nodes are equivalent, then the closeness centrality and the betweenness centrality in this case is going to be exactly the same. But one thing that we can do is to pick at random two links, okay? So we are going to pick a random like this link, okay, this one, and also another one here, I don't know, like this one. The larger the number of nodes, the better, okay? And then we are going to switch and this one, for instance. And then we are going to switch these two, the ends of these two nodes. So I'm going to exchange the ending of this link here, and I'm going to choose this one, for instance. And then I'm going to interchange the endings, okay? I'm going to swap the endings of these links. So in the end, what I'm going to do is that the degree is going to be the same, okay? I'm not going to change the degree of any of the nodes, but now the network is not going to be so regular. Not topologically, the degree is going to be regular, okay? It's going to be constant, but not the network topology. So we are going to have nodes that are slightly different. And when you do that, if you compute the closeness centrality and the betweenness centrality of this of the whole network, you are going to see now that there is some rank, okay? So we don't have that closeness centrality nor betweenness centrality are going to obtain, we are going to have the same, so now we have different values. We are not going to have the same result for all the nodes. And that's it. I'm going to upload to Moodle a notebook for closeness in K-regular networks. Where you can see that this is the case, okay? Yeah, this is exactly the case. And that's it, we are done with the exercise.